All right, this is 2019 number 6. Let's just read through it. Okay, so first of all, it tells us functions f, g, and h are all twice differential. That means they're continuous as well. And they're telling us that g of 2 and h of 2 are actually the same value. They're both 4. And that this line right here is tangent to both of those graphs, both the graph of g and the graph of h at 2. So not only does it hit this point 4, but they're both tangent to those points. So let's go ahead and attack part A then. If I go to this slide, we can just look at A and B together because they're kind of related. And remember that for something to be tangent, look, the tangent slope, that has to equal the derivative, right? If that equals the derivative, look what they're asking for right here. They want h prime of 2. Well, they're basically saying, what's the derivative of h at 2? We already know that this is the tangent line right here. Therefore, that must be the tangent slope. That's it. So this is just 2/3. That's all you have to do for that part A. Should be super easy. Should recognize that that right there is a slope. And therefore, that is h prime of 2. It's also g prime of 2 because it's tangent to both of those. We'll come back to that I think, in part D. All right, so let's do part B together. I know the B kind of got cut off here. Now it says, let a be the function given by 3x cubed times h of x. Write an expression for a prime of x. And then find a prime of 2. Okay, well, the first thing you should recognize right here is that this is a product of two functions. We have 3x cubed times h of x. So this is the product rule. And remember, the product rule basically says if you have some function that's a product, let's call it something, let's just say y equals a times b, then that means that y prime would equal a prime times b plus a times b prime. So what is a prime of x then? A prime of x would be the derivative of a, and a in this situation I'm just going to be as 3x cubed, so that would be 9x squared, you use the power rule, times good old h of x, plus normal a, which is just 3x cubed, times the derivative of h, which is just h prime of x. No chain rule or anything here, it's relatively simple. So we got an expression for a of x, that's actually part of our answer right there. We could box it or just underline it or something. But now we need to do a prime of 2. Well, if we plug in a 2, I would get 9 times 2 squared times h of 2 plus 3 times 2 cubed times h prime of 2. Okay, let's simplify this out. Well, this is 2 squared is 4. 4 times 9 is 36. And h of 2, what's h of 2? Well, they told me up here that h of 2 is 4. So I'm just going to go ahead and say parentheses 4 plus 2 cubed is 8. 8 times 3 is 24 times h prime of 2. Well, we just found h prime of 2 on this last problem. It's 2/3. So 2/3. Okay, 4 times 36. I don't know if you know that off the top of your head, but kind of something that I do here to kind of, I don't know, make it a little bit easier is I kind of break down the 3 and the 36. And one of the easy ways to break that down is actually 12 times 3. So if you did 12 times 3 times 4, isn't 3 times 4 12? And 12 times 12 is 144. Just kind of a way that you could get that answer in your head. All right, the next part, how do you do 2/3 times 24? Well, I'll tell you what I would do. I would make this 24 times 1/3 times 2, because that's really the same thing. And 24 times 1/3 is 8, and 8 times 2 is 16. All right, so I got 144 plus 16. That's 160, and so we could say that a prime of 2 is 160. All right, so A and B are done. Easy peasy, nothing really to it, simple stuff. Let's go on to part C. All right, part C is definitely a little bit of an interesting problem. It says the function h satisfies this function, x squared minus 4 over 1 minus f of x cubed, when x doesn't equal 2. It's known that the limit as x approaches, this is very important right here, the limit as x approaches 2 of h of x can be evaluated using L'Hopital's. Okay, so right away, L'Hopital's, remember, basically that means in order for it to use L'Hopital's, we have to get something indeterminate, right? So to use L'Hopital's, looks like hospitals, we need to, when we evaluate the limit, we need to either get like 0 over 0 or infinity over infinity or like 0 to 0. Okay, well, since we already see that this is a fraction, what I'm seeing then is that if we were to plug in a 2 to this, we should get 0 over 0. And that actually gives us quite a bit of information. So basically what we're saying is, if you were to plug in a 2, we should get 0 over 0. And let's just see what we get there. If I plug in a 2, I get this on top, and that definitely gives me a 0 on bottom. And 1 minus f of 2 cubed should somehow give me a 0 on the bottom. Well, if that's the case, let's just think about that. That means that that equals 0. Okay, if that equals 0, what else do we know? Well, we know that, I'm going to zoom in here. We know that 1 minus f of 2 cubed equals 0, which is the same thing as saying 1 equals f of 2 cubed. Okay, could I take the cube root of both of these? Yes, and I just found out that f of 2 has to equal 1. Okay, that'll be important because if you look at this problem, what does it say next? It says use the limit as x approaches 2 of h of x, which is essentially what we just did. We said, you know, we knew that the limit of this thing, we could use L'Hopital's. In order for us to use L'Hopital's, we'd have to get some indeterminate. So I just went ahead and set this thing equal to 0 over 0. And we solved, and we found out that f of 2 is 1. Okay, so we actually have part of the answer already. And we also need to find f prime of 2, show the work that leads to your answer. Okay, well, we got f of 2. So let's think about f prime of 2. Well, in order to get anything that has f prime of 2 in it, I'm going to have to take the derivative of this somehow. And so what involves the derivative and L'Hopital's rule? Okay, so let's think about this for a little bit. We're going to have to kind of go back in time and think about what L'Hopital's says. L'Hopital's says that if you're taking the limit of something, I'm just going to, let's say h of x, and let's say h of x is actually comprised of two functions. We'll call it a over b, capital A over b. And you're taking the limit of that. Well, that's going to equal the limit. If it's L'Hopital's, if you can use L'Hopital's, it would equal the limit would be the same thing as if you took the derivative of the top over the derivative of the bottom and then did the limit of that. So it should be the same thing. Well, they already told us that we can use L'Hopital's. So right away I'm thinking, okay, so I should be able to just take the derivative of the top, the derivative of the bottom, and then take the limit of that. So again, remember, I'm taking the limit of this whole thing, so that means I can take the limit as x approaches 2 of, instead of x squared minus 4, I could do a 2x minus 0 over, the derivative of 1 is 0, and the derivative of f of x cubed. Well, wouldn't that be minus 3 parentheses f of x squared? And then I need to think about something because I just took the derivative of a function, right? So I need to account for the chain rule. So I'm going to need to multiply this by f prime of x. Okay, and that limit should equal the same thing that the previous limit equals. We actually already know what this limit equals. So that's important for us to recognize too. They told us at the very beginning what this limit equals. I don't know if I mentioned that or not, but if you go back to the very beginning of the problem, it says that h of 2, it said it up here, that h of 2 equals 4. That's very important because if h of 2 equals 4, then that means that the limit as x approaches 2 of h of x also equals 4. That has to be the case. The reason why we know that's the case is they tell us it's twice differentiable, so we know it's continuous. We don't have any jumps or anything like that. We don't have any weird situation where there's nothing like a hole and then a different value here. That's not what's going on. What's going on is we might have something that fills a hole, so it's continuous. So this has to be true. Okay. Now that we know that's true, let's just set this equal to 4, right? And if I go to evaluate this limit now, I would have, remember I can just take the 2 and plug it in. So I'd have 2 times 2 minus 0, which is just gone, over negative 3. Basically, I have f of 2 squared times f prime of 2. And all of this equals 4. And you can kind of think this is 4 over 1, because what do you really get here? Isn't that just 4? And so if you have a 4 on top and a 4 on top, couldn't we kind of just say, okay, the bottom has to equal 1. All right, well, let's keep going with this then. I'm going to try and zoom in so I can have plenty of space to work with this. So if that equals 1, let's just do some basic algebra. We actually already found out earlier, where's it at? We found out that, sorry, it's all clunky. We found out that f of 2 equals 1, so I could just plug in a 1 there. I already know what f of 2 is. So I got negative 3. F of 2 is really 1 squared times this elusive f prime of 2 that I'm trying to find, and that has to equal 1. Well, this is not that bad. You got negative 3 times 1, which is really just negative 3, times f prime of 2 equals positive 1. Let's just divide both sides by negative 3. And you get f prime of 2 equals negative 1/3. Okay. It's a little bit, my work has been a little bit, I don't know, jumbled here, I would say, to say the least. So if you got more questions about this one, that's fine. Just hit me up or let me know if you want to talk about it in the Zoom session, we can. But basically, it's about knowing all the rules of L'Hopital's, and you're kind of like using the fact that L'Hopital's means it has to be indeterminate to get the first part, and the fact that we already know what the limit is. Even though they don't directly tell you that, you should just know, because it's continuous, that the limit is going to be the same thing. The limit is the same thing as the actual function. And then just set it equal and solve, okay? So this is a very unique L'Hopital's question. I haven't seen other ones like this before. All right, let's go on to part D. All right, this is the last one. It's known that g of x is less than h of x for 1 to 3. Let k be a function that's in between these three. All right, I want to point something out real quick. We've seen this only like one time before. It's very, very infrequent that we see something like this. And the only time we've ever even seen anything like that is for that good old squeeze theorem. I don't know why I did capital Q. I don't know why. Okay, so I have a feeling we're going to be using the squeeze theorem here. So let's just think about this. And it's true from between 1 and 3. And is k continuous at x equals 2? Justify your answer. Well, here's what we could kind of do. We could kind of say, all right, you know what? If I was to take the limit as x approaches 2 of all these things, of g of x and of k of x, because essentially I'm trying to find out if this limit, remember, if it's continuous, then that means that the limit exists. So if we could find out whether the limit exists, then we can determine whether or not it's continuous. If the limit exists, then it's continuous, right? So I'm just going to take the limit as everything as it approaches 2, which is what I'm trying to find out. Let's see, the last one is h of x. Okay. And we already know both of these. Remember the same idea. Because they told us at the very beginning of this problem, they told us that g of 2 is the same thing as h of 2 and that they both equal 4. So that means the limit as x approaches 2 of g of x is 4. And the limit as x approaches 2 of h of x is 4. And so therefore the limit as x approaches 2 of k of x, sorry, put an x there, must be between 4 and 4. Well, the only way, that's what squeeze theorem is, the only way it could be between 4 and 4 is if it actually is 4. All right, so if it is 4, therefore k is continuous at x equals 2 because otherwise it wouldn't exist. Otherwise the limit would not exist. Hope that makes sense. All right, see you guys on the next one.